Welcome to Eaton's Variable Frequency Drives 101. How do customers control industrial motors? Well, traditionally, customers use our trusty friend, the full voltage starter, which applies the full line voltage to the motor when it turns on. When a full voltage start is too harsh or accelerates too fast, we could use a soft starter to reduce the voltage sent to the motor and slowly ramp it up to full voltage. But with both of these controllers, once we get to full speed, the motor is stuck there until we turn it off. In order to change the motor's speed, we can use a magical box called a variable frequency drive, or a VFD. You may have heard it called a variable frequency drive, an adjustable frequency drive, a variable speed drive, an inverter drive, or often just the term drive, but they're all referring to the same thing. When a customer uses a drive, the power comes from upstream, which we can call the utility power. First, it passes through a circuit protective device, like a circuit breaker, and then it continues into the input of the drive. The frequency of this power is at 60 Hz. When the power exits the drive, it then continues to the motor. If we wanted to run the motor at full speed, the drive would supply the motor with 60 Hz. But if we want to slow down the motor, the drive is able to cut the frequency down to, say, 20 Hz, which causes the motor to run much slower. Or we can bump it back up to a faster speed at, say, 40 Hz. The drive allows us to have full control over the speed of the motor anytime we want. In order to better understand how this works, it will help to understand how the frequency of the power affects a three-phase motor. Back in the late 1800s, a sharply dressed Serbian named Nikola Tesla invented the three-phase AC motor. Not bad. In his design, there are two main parts: the stator and the rotor. The stator is the portion around the outside of the motor, made of lots of windings of thin copper wire. With a three-phase motor, there are windings that are specifically powered by the A phase, windings for the B phase, and windings for the C phase. The rotor is in the center of the motor and is the portion that spins when the motor is turned on. The rotor is also attached to the motor shaft, which connects the motor to whatever it's running. Let's look at the inside of the motor to understand how it operates. When the A phase enters the windings in the motor, the electricity flowing causes one set of windings to be positive and the opposite set of windings to become negative, thus creating a magnetic field between them. On the right-hand side, you can see the sine wave pattern of the power coming into the motor. Now let me slow it down for a minute. When the positive side of the sine wave is strongest, then the windings on that side become positively charged and the opposite side is negatively charged. When the negative side of the sine wave is strongest, the polarity inside the motor reverses, making the opposite windings positive and negative. The rotor in the center is magnetically charged as well, and it tries to align itself with the magnetic field being generated by the stator. But with only one phase going, it makes for a pretty choppy spin of the motor. Let's add in the B phase. I'll slow it down so you can see that as the A phase loses strength, the B phase gains strength and keeps the magnetic field moving. To make it nice and smooth, let's add in the C phase, which fills in the gaps when the A and B phases lose strength. Now, as the power continually comes into the motor, the switching back and forth of the AC sine waves causes the magnetic field to appear to spin. The faster the sine waves enter the motor, the faster the magnetic field spins. The slower the sine waves enter the motor, the slower the motor will spin. So let's crank this up to full speed and feed the motor with the full 60 Hz power being generated by the utility. Our buddy Nick Tesla is starting to get dizzy. So how do we slow down the motor? If we can stretch out those sine waves so that less of them are entering the motor per second, thus lowering the frequency of the power, then the magnetic field will spin slower. Since the utility is always pumping out 60 Hz, let's see if we can change that frequency. Inside of a drive, it can be broken up into three main parts. The AC power from the utility enters the drive and is converted from AC into DC. Then the DC is carried over and converted from DC back into AC. These three parts are called the converter section, the DC bus, and the inverter section. That seems like a lot of work to take AC power, mess around with it, and then spit it back out. So let's figure out why. In the converter section, we have nice clean AC power coming from the utility on one side, which looks like this. Inside the converter, there are diodes that chop up that AC power and spit it out as DC. We use capacitors inside the drive to smooth out this DC so that the power looks kind of like this. When it's on, it's flat until it turns off. Then the DC power gets onto the DC bus, which carries it over to the inverter section. Inside the inverter, there are small circuit board components called insulated gate bipolar transistors, which, as you can imagine, everyone calls IGBTs. The IGBTs act as little triggers that take the DC power and fire it out in short bursts. So, the IGBTs spit out the DC in a short burst, then another, then another. Then they let out the DC a little longer, and then a little longer, and then a little longer, and then a little shorter. Then they take the DC and flip the polarity. The DC is turned on and off, pow, 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 pow. Then it flips back. Then it flips again. What is this starting to look like? Yeah, a really lousy looking sine wave. Well, with the spacing of the bursts of the DC, the usable power in there averages out to look something like this to the motor. It's not perfect, but motors are dumb, and it's close enough to AC that the motor doesn't really know the difference. Why is this cool? Well, if the IGBTs can control how often and how long you spit out the DC, then you can space them out or tighten them up to effectively change the frequency of our imitation AC sine wave. This imitation sine wave coming out of the inverter is called pulse width modulation, or PWM. Since we know from our earlier conversation that changing the frequency going to the motor will change the speed of the motor, now we have a way to control that frequency. Pretty cool technology, but let's see how we can apply it. Why would you want to change the speed of the motor? Well, consider this example of a large ceiling fan in this manufacturing facility, used to keep the employees cool. With the motor running at our standard 60 Hz, the fan is spinning at full speed. This may be great for the middle of summer, but not so great for the middle of winter. When the temperature is cooler and the full capacity of the fan isn't needed, we can use a VFD to lower the frequency of the motor to a more appropriate fan speed. Our fan example is what's called a variable torque load. As the fan speeds up, the amount of torque or force required to move the air increases. Other types of variable torque loads besides fans are blowers, spinning pumps, and spinning compressors. The general rule of thumb is that if the load being moved is air, or a relatively easy to move liquid like clean water, then it's likely a variable torque load. Every drive needs to be able to supply the motor with its full load amps, or FLA, in order for the motor to run at full speed. But if the load changes or encounters extra load momentarily, we need the drive to handle the extra current draw from the motor without shutting down. Since you never really encounter chunky air, or if you're moving clean water, both are consistently smooth, so you don't need to have much extra capacity over the motor's FLA. So with a variable torque load, we size the drive so it has the ability to pump out 110% of the motor's FLA for a brief period of time. We call this a drive with low overload capability, as it's able to provide 110% of the FLA. If the load is not variable torque, it's likely what's called a constant torque load. Constant torque loads require the same amount of force to move the load at slow speeds as it does at higher speeds. Examples of constant torque loads are conveyors, elevators, shredders, or extruders that extrude the pasta that you buy at the grocery store. Basically, any load that isn't a fan, pump, blower, or compressor. Since constant torque loads can change frequently, like more boxes being added to a conveyor belt, the drive must be able to handle brief periods of extra current drawn by the motor. So to give the drive enough extra capacity, we size it 150% of the motor's FLA for constant torque loads. We call this a drive with a high overload capability, as it can provide 150% of the FLA. Let's come back to variable torque loads for a minute. Variable torque loads are kind of special because of how fluids like air or water move. They behave according to a law of physics called the affinity laws. The affinity laws state that as the speed increases with a variable torque load, so does the flow of air or liquid at a linear rate. So if the pump is running at 50% speed, then the flow of water is 50%. If you compare the speed against the pressure in a pipe or duct, the pressure increases at a rate of the speed squared. If you compare the speed against the power required to move the air or liquid, the power is equal to the speed cubed. This is the best part. Because of this relationship, if I'm able to run my motor at a reduced speed with a variable torque load, I consume substantially less power. Let's say I drop down to 70% speed. Well, then I only require roughly 35% of the power that was required at full speed. That difference in power required is energy savings on your electrical bill. The equation for figuring out the power required at different speeds is pretty simple. The power is equal to the percent speed cubed. So with my previous example, if I plug in 70% of full speed, or if I were using a calculator, I'd want to use 0.7 to represent 70%. Then I multiply 70% times 70% times 70%. And I end up getting about 35% of the power required at full speed. So if a customer is able to run their fan below full speed, then the savings start to roll in. Now that we know the basics of VFDs, regardless of size, shape, or color, they all work behind the same general principles. The power going into a VFD is fixed at 60 Hz, but the VFD allows us to adjust the frequency and the voltage entering the motor, which gives us full speed and torque control anytime we want. The type of load we put on the motor can affect how we size the VFD, and with variable torque applications, we see significant energy savings while running below full speed. That concludes our lesson on variable frequency drives. For more training opportunities and resources, please visit the Electrical Training Group's website at www.eaton.com/training.